So hi everyone, so good afternoon all. So Alok Kumar, good afternoon dear. Okay, so first of all, let me know whether audio and video everything clear, right? Okay, so if audio and video is not clear, please give some comment in live chat box. Okay, so otherwise we will continue here. Okay, so we are dealing with the subject electromagnetics, and we are dealing with the topic electrostatic potential energy. So Rajat Hazara, good afternoon. Anand, okay. Okay, so electrostatic potential energy, we are dealing with electrostatic potential energy. So here I will give you some conclusions here. Okay, so these conclusions are very important. So whatever we have done up till now, so for that I am giving conclusions here, right? Okay, see, so I am categorizing into two cases here. So case 1, so in case 1 so what we have done here, we have taken some charge distribution. So whenever you consider some charge distribution, it is going to set up some electric field in its vicinity. So that field is going to exert the force on other charge carriers. So whenever you try to take any charge carrier into this field, then that field is going to exert a force on that charge. So against that force, if you try to move that charge in the field, then you have to do some work. So whatever the work you are doing, that will be stored as what? That will be stored as potential energy. Yes or no? So during this process, what we have assumed here, we have assumed that the velocity of the charge is almost or approximately equal to what? Approximately equal to 0. That means you have to maintain the velocity as constant here. Okay, so since initially at infinity we have assumed that the velocity of the charge is 0, that means it is at rest. We have assumed that the charge at infinity is at rest, so that means its velocity is 0. So that means in order to maintain the same velocity, what you have to do, so you have to move that charge very slowly, such that we can approximate its velocity is equal to what? 0. So what happens whenever the velocity is approximately equal to 0 here? So whenever the velocity is approximately equal to 0, that means I am assuming that here there is no change in velocity. Yes or no? So I am assuming here there is no change in velocity. Right? Okay, so whenever there is no change in velocity, so what is the change in kinetic energy here? The change in kinetic energy is also approximately equal to what? Approximately equal to 0. So whenever there is no change in velocity, so from this relation here, that is force is equal to what? Mass into acceleration, that is mass into dv by dt. So the net force, if there exists any net force on an object, then that object has to experience some change in velocity. Yes or no? Or it is going to accelerate. Since here there is no change in velocity, that means dv by dt will go to 0. So that means here in this case the net force here is equal to what? Is equal to 0. So that means approximately equal to 0. So we can equate it equal to 0. Understood? So whenever net force is equal to 0, so what are the forces that are acting on the charge here? What are the forces that are acting on the charge? So the forces that are acting on the charge is one is electrical force and another one is what? External force. Yes or no? So those are the two forces acting on the charge. So the net force is nothing but F external plus what? Plus F electrical must be equal to what? Must be equal to 0. So from here, therefore F external is equal to what? Minus F electrical. Understood? Okay, see why we have made all these assumptions here? Why we have made all these assumptions? Why? Why we have considered there is no change in velocity and all these things? See, in this case, we don't know what is the external force that we are applying. Yes or no? We don't know what is the external force that we are applying in order to move the charge. Okay, so in that case, how you can determine this external force here? It is not possible to directly determine that external force what you are applying. Understood? Okay, so that's why if we make this assumption, then the net force acting on the charge will become equal to 0. In that case, the external force will become exactly equivalent opposite to what? Electrical force. Understood? And we know how to determine this electrical force. Understood? Thus, we can determine the work done by the external agent. Yes or no? So, in this case, what is the work done by the external agent here? What is the work done by the external agent? So, the work done by the external agent in moving the charge from infinity to r is equal to what here? Is equal to r to infinity. Yes or no? R to infinity. We have already derived all these things here. Fe bar dot dr bar. So, actually speaking, this is nothing but what? Integral infinity to r f external dot what? Dot dr. So, because of these approximations, we can calculate f external as what here? F external is nothing but minus f electrical. So, if you substitute in place of f external, if you substitute minus f electrical, then you are going to get this expression. Understood? Okay. So, I hope you have understood all these things here. Okay. Okay. So, this is the work done by the external force in order to move the charge from infinity to r. Understood? Okay. So, now if you want to determine the work done by the field force here. So, if you want to determine the work done by the field force in moving the charge from infinity to r. So, in this case, what is the work done? Tell me. Now, let us assume here you are having some capital Q. So, at far away you are having small q. So, you are trying to move this charge in this direction. Understood? Okay. So, whenever you are trying to move this charge in this direction, so you have to apply external force in this direction, and field force is going to act in this direction. Understood? Okay. Okay. Yeah. So, integral, you are moving from where to where? From infinity to what? From infinity to r. So, integral infinity to r. So, you want to determine the work done by the field force. So, field force is acting in this direction and the charge is moving in this direction. Yes or no? Okay. So, the charge is moving in which direction here? From infinity to r, but the field force is acting in which direction? From r to infinity. Understood? Both are opposite to one another. Remember that. So, F electrical dot dr bar. F electrical dot dr bar. So, in this manner I can write. Yes or no? Okay. So, this is the work done by the field force. What is the work done by the field force in moving the charge from infinity to r? That is nothing but infinity to integral infinity to r F electrical dot dr bar. Understood? Okay. See, both the work done by external agent and the work done by the field, both I have represented in terms of what? Both I have represented in terms of electrical force only. Understood? Why means I don't know what is the external force you have applied. So, with these assumptions, I have concluded that F external is equal to minus F electrical. Understood? So, by substituting this, I got these expressions. Understood? Okay. Okay. Yeah. So, just to follow the concept here, that's it. So, if you just follow the concept, you will get the answer. Okay. So, there is no need to remember anything here. There is no need to remember anything. Right. So, in general, in this case, in general, they are not going to ask you to determine the work done by the field, or they don't mention in general work done by the field or work done by the external agent like that. Okay. So, by default from here onwards, whenever I say work done, it is by default work done by what? Work done by external agent. So, from here onwards, by default, we are going to consider what here? We are going to consider work done by what? Work done by external agent. From here onwards, by default, we are going to consider always work done by what? Work done by external agent. See, if you know work done by external agent, if they ask to determine work done by field force, then also you can determine or not, yes or no. See, in this case, one more thing is the work done, the total work done or the net work done, the total work done or net work done in this case is equal to what? Is equal to 0 or not, yes or no. We have derived all these things here. So the net work done or total work done in this case is equal to 0. The net work done or total work done means what? The work done by external agent plus the work done by the field. So if you add up these two, you are going to get what? 0. Understood? Okay. Okay. Yeah. So from here we can say W external plus W field must be equal to what? Must be equal to 0. So from here W external or W field. So if you want to determine work done by field, then that must be equal to what? Minus of W external. So there is no need to determine both here. Okay, so if you determine one thing, then automatically you can get the other. But in general, in most of the things here, 99% they are asking to determine the work done by what? Work done by external agent. So if they have not mentioned anything, then by default we blindly take the work done by what? Work done by external agent. Understood? Okay, so these are the conclusions we can make in case 1. So what is case 1 here? So the velocity is approximately equal to 0. Why we are making this assumption? So if you make this assumption, then only we can determine this external force. Understood? Okay. So if velocity is not changing, then change in kinetic energy in this process will be equal to 0, and the net force acting on the charge will be equal to 0. So if the net force is equal to 0, then external field force can be written as what? Minus of F electrical force. So in this case, the total work done or net work done by all the forces will be equal to 0. Understood? And hence, if you determine work done by the field or work done by the external agent, if you determine one thing, then automatically you can determine the other also. But by default, we always consider work done by what? Work done by external agent. So here I have given the expressions how to determine work done by external agent and work done by the field force. Understood? Okay. Okay. Yeah. So this is case 1 here. This is case 1. So there is another case, that is case 2. Yes or no? So case 2. I am considering case 2. What is case 2 here? See, yesterday we have done one problem, yes or no? So here some Q2, this is one electron, so it is fixed at this location. So from far away distance from Q2, so Q1 is projected towards what? Towards Q2 with velocity V is equal to some 10 power 5 meters per second or something. Understood? Okay, so here there is no external force acting on this charger, just it is projected with some velocity. Initial velocity is 10 power 5 meters per second. So whenever with this velocity it tries to move towards what? Towards Q2. So that means it is entering into the field produced by Q2. So what that field will do? That field is going to exert a force on this Q1. Understood? So since both are of same polarity, it is going to be a repulsive force. So against that repulsive force, whenever this charge will try to move, then its velocity will gradually decrease. Yes or no? So as the velocity is changing, now in this case the velocity is changing. In case 1, the velocity is not at all changing. Understood? Okay, so here the velocity is changing. Understood? That means the kinetic energy is also going to change. That means the net force acting on the object is not equal to 0. Understood? So what is the only force that is acting on this charge here is nothing but the force exerted by what? The exerted by the field produced by Q2. Understood? Only field force is acting on this charge. No other forces are acting on this charge. Understood? Okay, so this is case 2 here. This is case 2. So in this case 2, so what are the conclusions we have drawn? So here there will be a change in what? There will be a change in velocity. So there will be change in velocity. So this is the first point. Yes or no? So if there is a change in velocity, then what will happen here? What will happen? There will be a change in kinetic energy. So the change in kinetic energy is not equal to 0. Next, Next, the net force acting on the object is not equal to what? Is not equal to 0. See, whenever the net force acting on the object not equal to 0, then only that object is going to have acceleration. Acceleration means what? Change in velocity. That means whenever net force acting on the object is not equal to 0, then only that object is going to have acceleration. That means then only it is going to have change in velocity. Understood? Okay. So change in velocity means there will be a change in kinetic energy, and the net force acting on the object will be not equal to 0 in this case. Now, in this case here, we have seen one more thing, that is the total or net work done. The net work done or total work done is not equal to what? Is not equal to 0. So these are the conclusions. These are the conclusions we have drawn. Understood? Okay. Now, in this case, how we have solved this problem here? So here you have Q1 and here you are having Q2. So it is projected here. So with velocity 10 power 5 meters per second. So how we have solved this problem? We have applied law of conservation of energy or not? Yes or no? So initially, what is the total energy of this charge? The total energy is nothing but what? Is nothing but potential energy plus kinetic energy. But since this charge is very, very far away from Q2, so the potential energy will be 0. It is going to have only kinetic energy. So the total energy is in the form of only kinetic energy initially. So now, as this charge moves towards Q2, what will happen here? Because of this repulsive force, its velocity is going to change. That means the kinetic energy gradually decreases. So whatever the decrease in kinetic energy, that will be transformed into what? Potential energy, such that always the total energy must remain what? Must remain same. Understood? So that is what is called as what? That is called as what? That is called as law of conservation of energy. Understood? So here in this case, what we have applied here? What we have applied? Law of conservation of energy. Understood? So this is nothing but law of conservation of energy. Conservation of energy. Understood? Law of conservation of energy. So what do you mean by law of conservation of energy here? So the total energy here. So the total energy in the system. The total energy in the system must be constant at any instant of time. At any instant of time, the total energy in the system must be constant. That means it should not change. Understood? Okay. So as the charge is moving, as Q1 is moving towards Q2, the kinetic energy is decreasing, but whatever the decrease in kinetic energy, that is transformed into what? Potential energy, such that the total energy will remain what? Will remain same at any instant of time. So that is called as what? Law of conservation of energy. So the total energy should not change with respect to time. So that means if I differentiate this here, if I differentiate this with respect to time, what I have to get? I have to get this equal to what? This equal to 0, because total energy should not change with respect to time. That means total energy must be constant with respect to time. So if you differentiate total energy with respect to time, then it must be equal to 0. Understood? So this is called as what? Law of conservation of energy. Now here the total energy will be in the form of what here? Will be in the form of either potential energy and kinetic energy. It is in the form of potential energy and kinetic energy. Yes or no? So the total energy I can represent as what here? See, here we are talking about conservative fields here. Here we are only talking about conservative fields. We are not talking about non-conservative fields. Understood? So keep always that point in mind. Only for conservative fields, this potential energy concept, potential and everything is valid. Understood? Okay. Okay, yeah. So now here I can write this as d by dt of potential energy plus what? Kinetic energy is equal to what? Is equal to 0. Now I can write this as d by dt of potential energy is equal to what? Is equal to minus of d by dt of kinetic energy. So can I write in this manner? Yes or no? So d by dt of potential energy is equal to minus of d by dt of kinetic energy. Understood? Okay. So now what I am going to do here is I am going to integrate on both sides. I am going to integrate on both sides with respect to time here. With respect to time. So if I integrate on both sides with respect to time, so with respect to time from initial position, from initial time to final time here. Okay, so here I am integrating, so this is the, so here this is the initial position and this is the final position, yes or no? Okay, so I am integrating from initial to final, understood? Now here dt will get cancelled, here dt will get cancelled, so integration of d of potential energy is nothing but what? Here differentiation and here integration will get cancelled, so you will get potential energy. So if you substitute the range, what you are going to get? Potential energy final minus what? Potential energy initial, understood? So this is equal to what? This is equal to minus of what? Minus of, so here differentiation and integration will get cancelled, so you will get, if you substitute the range, you are going to get kinetic energy final minus what? Kinetic energy initial, understood? Okay, so potential energy final minus potential energy initial must be equal to minus of kinetic energy final minus kinetic energy initial, understood? Okay, now if you take if you rearrange these terms here, how you can write? Tell me. So potential energy final plus kinetic energy final must be equal to what? Must be equal to kinetic energy initial plus what? Plus potential energy initial. So this is the total energy, yes or no? So this is the total energy, initially. So initial total energy is equal to what? So this is, sorry, this is final, no? Sorry. So this is the total energy, final total energy, and this is nothing but what? This is nothing but the total energy initial, understood? Okay, so by doing this one, by equating these two, so we have determined, we have solved this problem or not, yes or no? So that is second case, so this problem, understood? Okay, so always all this analysis and all these things are very, very important here. So these are the concepts here. Okay, so if you are familiar with these concepts, then you will never ever confuse while doing the problems, understood? Okay, so I hope all these things are crystal clear, right? Okay, yeah. Okay, so let me know this case 1 and case 2, both are clear or not? Yes or no? Yeah. So Paras Moon, Rajat Hazra, Alok Kumar, tell me here, is everything clear? I hope these two cases, you should not confuse between these two cases here. I hope these two cases are clear. Yes or no? Okay. Okay. Next. So next is electrostatic potential. Electrostatic potential will represent with V. Okay. So those two cases are clear. Tell me here. Paras Moon, Anand, Alok Kumar, Rajat Hazra. Tell me here. Yes. Okay. Okay. So next is electrostatic potential. See, if you understand electrostatic potential energy, then there is nothing here to understand electrostatic potential. You can easily understand electrostatic potential if you understand electrostatic potential energy. Yes or no? Okay. Okay. Now see here. Okay, so here the work done, I don't write every time external here. From here onwards you have to understood that whenever I am writing work done, it is the work done by the external agent. Yes or no? Okay, so by default whenever I am writing W, you have to consider that work done by external agent. So every time I don't write external. Understood? Okay, so the work done, so for the first time I am writing here, from next onwards I don't write. Okay, so the work done by the external agent in moving the charge from infinity to R is equal to what? Is equal to integral R to infinity F electrical dot what? Dot dr bar. Right? Okay. Okay, yeah. So now here what I am doing here is, here I am dividing this with Q and multiplying with what? Multiplying with Q. So now we know that force per unit charge here, we know that force per unit charge is nothing but what? Is nothing but electric field. Yes or no? Okay. So what? Alok Kumar, please solve some more gate questions so that you can make our concepts more clear. I will solve here, don't worry. See, first of all, we have to get familiar with the concepts now. So once you get familiar with the concepts, then we can solve the problems, right? Okay. Okay. So here, in the previous session, I have solved the problems based on electrostatic potential energy, right? Yes or no? Okay. So today I am starting this electrostatic potential. So once we complete this concept, then we'll solve some more problems, right? Okay. So work done by the external agent in moving the charge from infinity to R, I can write in this manner. So here what I am doing here, I am dividing with Q and multiplying with Q. So the force per unit charge, I can call it as what? I can call it as electric field. Yes or no? So I can represent the same expression as Q into integral R to infinity E bar dot what? E bar dot dr bar. So this is the work done. This is the work done by the external agent in moving the charge from where to where here? From infinity to R. Understood? So okay. So this is the work done. This is the work done by the external agent in moving the charge from infinity to R. So what is the charge? What is the charge we have moved here? That is nothing but Q amount of charge. So we have moved Q amount of charge in the field produced by some charge distribution. Yes or no? So we have moved a charge Q in the field produced by what? In the field produced by some charge distribution from where to where? From infinity to R. So then this is the work done by the external agent in terms of what? In terms of electric field. You can write in this manner. Okay, so this is the work done in order to move Q amount of charge. This is the work done in order to move Q amount of charge. Understood? Okay, so now here, see here. So whenever you have moved, so here you are having some charge distribution. CD means charge distribution here, right? Okay, so whenever you are moving some Q amount of charge into this field here, into this field, okay, from infinity to some distance R, okay. So whenever you are moving this charge Q, from infinity to R, so you are doing what? You are doing some work. So whatever the work you are doing, that will be stored as what? That will be stored as potential energy. See, for example, let us say this charge distribution is, let us say capital Q. Understood? So you have taken small q from infinity to this location. Okay, let us say the distance from here to here is R. Understood? Okay, so now in this case, what is the potential energy here? What is the potential energy we got? So the potential energy, that is the work done in order to move the charge from infinity to R, what we got? QQ by 4 pi epsilon into R. Yes or no? Okay, so this is the potential energy at R with respect to what? With respect to infinity. So from where you have moved here? You have moved this charge from infinity. So at infinity here, what is the potential energy? What is the potential energy at infinity? So at infinity means, put here R tends to infinity. So the potential energy at this location, the potential energy at infinity is equal to what? Is equal to 0. The potential energy at infinity is equal to 0, and the potential energy, so the potential energy at R here, at this location R, is equal to what? Is equal to QQ by 4 pi epsilon R. QQ by 4 pi epsilon R. Yes or no here? Okay, so that means I can write, see, I have already told that this work done, we call it as what? We call it as potential energy. Yes or no? This work done, we call it as what? Potential energy. Understood? Okay, so here the as you move the charge from infinity to R, you have gained the potential or you have lost the potential. Here the potential energy at R is nothing but QQ by 4 pi epsilon R, whereas here the potential energy is equal to 0. So that means as you move the charge from here to here, you have gained a potential energy. Yes or no? So in general here, in general, we will consider what? We will consider always as gain in potential energy. So if we get this value as positive, then we treat it as gain. If we get this value as negative, then we treat it as what? We treat it as loss in potential. Understood? But always we call it as what? We call it as gain in potential. So depending upon whether it is positive or negative, we have to understood that whether it is gain or loss. Okay. Okay, so that means what I mean to say here is, so work done in order to move the charge from infinity to R. So if you move the charge from infinity to R, you are gaining the potential. Yes or no? So you want to know what is the gain in what? What is the gain in potential energy? If you want to know what is the gain in potential energy, what you have to do? You have to take the potential energy at R minus what? The potential energy at infinity. Yes or no? You are always considering the reference as what here? Reference as infinity. See, whenever you are saying gain or loss, you must have some reference or not. Understood? So here the reference is nothing but what? Infinity. So with respect to that reference, at this reference point, the potential energy is equal to 0 initially. So then what I have done? I have moved the charge. By applying external force. So from infinity to this location. So I have gained some potential energy. So while moving the charge, you have applied the force or not? You have applied some external force. Yes or no? So whatever the work you have done in moving the charge, that will be stored as what? That will be developed as potential energy. So that means as you move the charge from here to here, you have gained a potential energy. Now you want to determine what is the gain in potential energy. What is the gain in potential energy? So how you have to write here? You have to consider the potential energy at R minus what? The potential energy at infinity. Understood? Okay. So this is the gain in potential energy. If you want to determine the gain in potential energy, what you have to write? You have to write it as what? You have to write it as, so I am writing here, so external infinity to R, this is equal to what? Potential energy at R minus what? Potential energy at infinity. So this must be equal to what? This is equal to Q into integral R to infinity E bar dot dr bar. E bar dot dr bar. Understood? Okay. So this we always call it as what here? Gain in potential energy. So if this difference you got it as positive, then we will say gain. If this difference is negative, then we will say loss. That's it. Understood? Okay. Okay here. So this is the work done in order to move the charge from infinity to R. So in order to take Q amount of charge, from infinity to R, this is the work done. Then what is the work done per unit charge here? What is the work done in order to bring unit positive charge? See, the work done in order to bring Q amount of charge is this one. Understood? What is the work done in order to bring a unit positive charge? Or I can say, what is the work done per unit charge? Tell me, what you have to do here? What is the work done per unit charge? Tell me. Tell me here. So this is the work done in order to bring Q amount of charge from infinity to R. Now what is the work done per unit charge? Or what is the work done in bringing unit positive charge? In bringing unit positive charge from infinity to what? From infinity to R. Tell me here. What I have to do? Tell me. Alok Kumar, Parasmoon, Anand, tell me here. This is the work done to bring Q amount of charge divided by Q. Yes. Okay, so work done per unit charge is nothing but what? Is nothing but W external from infinity to R by Q. So by Q. So that is equal to potential energy at R minus potential energy at infinity divided by what? Divided by Q. So instead of potential energy at R and potential energy at infinity, you can write it as what? You can write it as potential energy we can represent with W. So WR minus what? Minus WP. So in this manner, W infinity. So in this manner also you can write here. Understood? Okay. Okay, so this is equal to what here? So if I divide with Q, then what you are going to get? Integral R to infinity E bar dot what? E bar dot dr bar. E bar dot dr bar. Okay. Alok Kumar, divide by Q. Yes, dear. Yes, very good. Okay. So, so the work done. So this is nothing but the work done per unit charge, or the work done in order to bring unit positive charge, or work done in order to bring unit positive charge. Understood? Okay. So this work done per unit charge, we call it as what here? We call it as potential. We call it as what here? We call it as potential. Okay. So what do you mean by potential? So potential, that is electrostatic potential here. This potential is nothing but electrostatic potential. So what do you mean by electrostatic potential? So the work done in bringing unit positive charge. UPC means unit positive charge. From where to where? From infinity to R. Okay. So electrostatic potential at any point is defined as what here? The work done in bringing unit positive charge from infinity to that point here. Okay. Okay. So now this is equivalent to, see here. So here this is the potential energy per unit charge. Potential energy per unit charge is nothing but what? Is nothing but potential. Potential energy per unit charge. Potential energy per unit charge is nothing but potential. So here this is nothing but what? This is nothing but gain in potential. Yes or no? So this is nothing but gain in potential energy. Gain in potential energy per unit. Gain in potential energy divided by what? Divided by Q. So that means this total represents what here? This total represents gain in potential energy per unit charge, which we call it as what here? Which we call it as electrostatic potential. So whenever I am representing electrostatic potential here, how I will represent? See here. So here potential energy at R. So here we are having potential energy at R by Q minus potential energy at infinity by Q. So this is equal to what? This is equal to integral R to infinity E bar dot what? E bar dot dr bar. Now the potential energy at R per unit charge, I call it as what? I call it as potential at R. So potential at R, that is VR minus W infinity by Q, I can write it as what? V infinity. Understood? So this is equal to what here? Integral R to infinity E bar dot dr bar. Understood? Okay. Okay. So finally I can write in this manner. So that is the work done by the external agent in moving the charge from infinity to R, that is the work done per unit charge, is equal to what? Is equal to, I can write it as VR minus what? VR minus V infinity, which is equal to integral R to infinity E bar dot what? E bar dot dr bar. Okay. So up till now, is this clear here? Up till now? Up till now, is this clear? So VR represents gain in potential at R okay. So R I will so once I will represent, then I will tell you. Okay. So first of all, let me know, up till here is everything clear? Up till now is everything clear? So what are the units of this one here? What are the units of this one? Tell me. Work done per unit charge. What are the units? Work done is nothing but joules per unit charge means by Q, that is coulombs. So what are the units? Units are nothing but joule per coulomb. Joule per coulomb, or we can say volt. Joule per coulomb or volt. Okay. So is there any doubts up till now? Tell me here, Parasmon. Tell me. Alok Kumar. See, let me know if you are having any doubt here. So if it is clear, then we will move on. Tell me, dear. Parasmon, clear? Okay. Okay. Okay, yeah. Now see here. Now generally where the students will get confusion means here it is VR minus V infinity. Understood? Okay. So here this is not here work done in order to move the charge, work done per unit charge in moving the charge from where to where? Infinity to R, infinity to R. So here it is VR minus V infinity R. So in some books here, in some books what they will do here is, so they will write it as VR infinity, VR infinity, where VR infinity is equal to what? VR minus V infinity. So in some books they will represent the same thing as VR infinity, VR infinity. So but they will consider, in some books what they will do is, they will write this one as V infinity R, V infinity R, and here they will write, still they will write VR minus what? VR minus V infinity. Understood? So in some books what they will do, VR infinity, they will represent this one here. See, in some books it is just like VAB. If you are having VAB, so in some books they will represent this as VA minus VB, and in some books the same thing they will represent it as what? VB minus VA. Understood? Okay. So they will write in some books they will write VB minus VA, in some books they will write VA minus VB. Understood? Okay. So here so that is their convention here, that is their convention. Okay. So you can follow any convention here, you can follow any convention. So here it is V infinity R, so they have written VR minus V infinity. Here VR minus V infinity they have represented as VR infinity. Understood? So both are correct only here, both are correct only. So the main thing is it should not change, that is VR minus V infinity. So here you have to get VR minus V infinity. That should not change. So you can represent this one either in this manner or in this manner, it doesn't matter. Okay. So what we will do here is we will follow any one of these conventions. So we will follow this one here, we will follow this one, right? Okay. See, if you understand the concepts, then everything will be fine here. Just it is matter of conventions, that's it. Okay. Okay. So now here I can write this as what? Integral VR infinity. I am representing this as what? VR minus V infinity as VR infinity. Understood? And this is nothing but the work done by the external agent in moving the charge from infinity to R, infinity to R by Q, work done per unit charge. Okay, so this is equal to integral r to infinity e bar dot what? E bar dot dr bar. E bar dot dr bar. So work done in order to move the charge from infinity to r by q is equal to what? V r to infinity. So here whenever you are moving the charge from infinity to r, so you have gained the potential. Yes or no? You have gained the potential at r with respect to what? With respect to infinity. So whenever you are moving unit positive charge from infinity to r, you have gained the potential at r with respect to what? With respect to infinity. So here always whenever you are representing here subscript, always here gain in r infinity will represent what here? Gain in potential. Gain in potential at r. Gain in potential at r with respect to what? With respect to infinity. So in this manner we have to represent. So where V r infinity, where V r infinity is equal to V r minus V infinity. Okay. So always we are writing the subscript in this manner, that is gain in potential at r. V r infinity represents what here? Gain in potential at r with respect to what? With respect to infinity. See, always remember the potential and potential energy must be defined with respect to some reference. With respect to some reference. Understood? Okay. So without any reference, we cannot define what? We cannot define potential energy and potential. Understood? Okay. So keep that point in mind here. So always the potential at any point, if I say the potential at some point, the potential at some point is something, means what do you mean by that? What do you mean by that? So you have gained that potential by moving the unit positive charge from infinity to that point. Understood? So always you have to measure the potential. You are measuring the potential at any point with respect to what? With respect to some other reference point. Understood? Okay. So potential at any point is nothing but what? Is nothing but the work done in order to move a unit positive charge from infinity to that point. From infinity to that point. Here in general we will consider the reference point as infinity here. So that's why I am specifying every time infinity, infinity. Understood? See, in general we will consider the reference point as infinity. Understood? Okay. 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 So here, okay. So here, if I want to determine, so I can write, now I can write this work done external from infinity to r is equal to, so send this q to this side here, multiply q with multiply with q here. So what you are going to get? Q into Vr infinity is equal to what? Q into integral r to infinity E bar dot what? E bar dot dr bar. Understood? Okay. Okay. So therefore that means work done by the external agent in moving the charge from infinity to r is equal to what? Q into Vr infinity. So where Vr infinity is equal to what? Where Vr infinity is equal to integral r to infinity E bar dot dr bar. Right. See, in general in some books what they will do here is instead of here Vr infinity, we are writing Vr infinity is equal to like this now. So they will interchange the range limits here. That means they will interchange this range here. So they will write this as infinity into infinity to r, and they will put here minus, and they will write here E bar dot dr bar. So this one and this one both are correct or not? Both are same. Both are one and the same. Understood? But in some books what they will do is they will put here minus, and here just they will interchange this range here. Okay, here you have written r to infinity, they will write infinity to r, and they will put here minus. Understood? Okay, but we have to follow only one convention here. If you follow one convention, then we are not going to do any mistakes. So we always follow this convention. Understood? Okay. So why unnecessarily put minus sign and change this ranges and all these things? So instead we can easily remember this one. Yes or no? Vr to infinity is equal to integral r to infinity. Okay. Okay. Yeah. So now so now you have to observe one more thing here. So here whenever you are writing work done, so work done, in order to move the charge from infinity to what? Infinity to R, you have to write it as what? Q into VR infinity, Q into VR infinity. Understood? Okay, so in this manner you have to write here. Now if I write this is initial position and this is final position, yes or no? So R is final position and this is infinity is initial position. If suppose they ask to determine the work done in order to move the charge from A to B here, suppose they have mentioned from A to B. Understood? Then how to write here? So A is nothing but initial and B is nothing but final. So this is equal to what? This is equal to Q into what? Q into, here whenever you are writing the potential, how you have to write? First you have to write gain in potential at R with respect to infinity. That means you have to write first final, you have to write it as subscript. Whenever you are writing subscript, first write on final and then initial. So that is VBA. Understood? So that is equal to Q into what is VBA? So integral B to A E bar dot what? E bar dot dr bar or dl bar, whatever you want you can write here, dr bar or dl bar. Okay, it has to represent the displacement, that's it. Understood? Okay, okay, yeah. So you can write in this manner. Okay, okay, yeah. So now what we have concluded here is, so if you are having the potential from A to B, potential from A to B, I can write it as integral A to B E bar dot what? E bar dot dl bar or dr bar, whatever you want you can write here. Okay, so the same thing I can write it as minus of integral B to A E bar dot dl bar. So in any manner you can represent here, it doesn't matter. So whenever you are taking the range here, we are very much clear when you have to take plus sign and when you have to take minus sign. That is if you interchange these limits, then you have to take minus sign. Yes or no? So we are very much clear when to take plus here and when to take minus here. Understood? Okay, okay, yeah. But now here if I write the relation between the potential and electric field without taking its limits here, that means if I write V is equal to integral E bar dot dl bar, I have written V is equal to integral E bar dot dl bar. So here whenever you are having limits here, we can easily say we are very much clear about positive signs and negative signs. Yes or no? But without limits here, if I just represent the relation between the potential and electric field in this manner without taking the limits. Understood? Then what you have to put here, whether you have to put here plus or minus sign. Tell me here. So I am not writing any limits here. So if you write limits, then it is very clear. Yes or no? Whenever you are writing the limits, then it is very clear. Understood? So now here I am not representing any limits. Okay. So now in this case here, what you have to write, whether you have to write plus sign or minus sign, we don't know that. Yes or no? So it may be plus or it may be minus. Understood? So we are trying to get the relation, the exact relation between what? Between the potential and electric field here. Okay, so we know that V and E are related in this manner. Okay, so I am not representing any limits. Okay, so then my doubt is whether you have to put here plus or minus. So that's what I want to find out. I want to find out the exact relation between V and E. Okay, so that is including what? Including the polarity, that is including the sign here. So what I will do here is, so I can write this one here, I can write this one as integral E bar dot dl, I can write it as E dl cos theta, E dl cos theta. So that is equal to V. Yes or no? Now what I will do is I am going to differentiate on both sides. So if you differentiate on both sides, what you are going to get? So dou V by dou L is equal to what? Is equal to dou by dou L into integral E cos theta into dl. Yes or no? So here differentiation and integration. Differentiation is with respect to L, integration is also with respect to L. So this differentiation and integration will get what? Will get cancelled. So you are getting what? You are getting dou V by dou L. Dou V by dou L is equal to what? Is equal to E cos theta. Dou V by dou L is equal to E cos theta. Now tell me, what is dou V by dou L? What is dou V by dou L maximum? What is dou V by dou L maximum? Tell me. What is dou V by dou L maximum? Tell me. Tell me here. Parasmoon, Alok Kumar, tell me. What is dou V by dou L maximum? What is dou V by dou L maximum? When this value will be maximum? Whenever theta equal to what? Dou V by dou L equal to E cos theta. When this dou V by dou L will be maximum? Tell me. Whenever theta equal to what? Whenever theta equal to 0. Yes or no? So whenever theta equal to 0, this dou V by dou L will become maximum. That is dou V by dou L maximum is equal to E. Is equal to E. Yes or no? Okay. Okay, yeah. Is this point clear here? Dou V by dou L maximum is equal to E. Yes? Okay, very good. So now here, so I got E is equal to dou V by dou L maximum. So now here potential is a scalar quantity or vector quantity? Tell me. See, potential, it is a resultant of what? Potential is a resultant of what? Resultant of this dot product or not? Yes or no? So resultant of dot product means potential must be what? Potential must be a scalar quantity. Potential must be a scalar quantity. Or I can say potential is a scalar field. Yes or no? Okay. So here this is a scalar field. So the slope of the scalar field is maximum, that is dou V by dou L maximum. So what it represents here? Tell me. Dou V by dou L maximum. So the steepest slope, it represents what? Steepest slope or maximum slope of the scalar field at a point. The steepest slope or maximum slope of scalar field at a point. So is nothing but what? Tell me. If you would have attended to my previous sessions, then you will tell this answer here. Tell me. Yes. So what do you mean by this? Tell me. Dou V by dou L maximum can be written as what? Yes, very good, very good. So it is nothing but gradient. Yes or no here? Okay. So I have already told here when explaining gradient, I have told yes or no, gradient of f is equal to what? I can represent it as dou f by dou L maximum. So the maximum slope or steepest slope of a scalar function at a point is nothing but what? Is nothing but gradient of that scalar function. Now here the scalar field or scalar function is nothing but potential. So the maximum slope or steepest slope of this scalar function at a point can be represented as what? Can be represented as gradient. So this I can represent it as what? So this I can represent it as gradient of what? Gradient of V. So now see here. So now so gradient of any scalar quantity, gradient of any scalar field, the resultant is nothing but what? The resultant is nothing but a vector quantity. And electric field is also a vector quantity. So on LHS we are having a vector quantity, on RHS also we are having vector quantity. Understood? But what do you mean by gradient of V here? Gradient of V is going to result in a vector quantity which points in the direction of what? Which points in the direction of maximum increase in the scalar potential. Yes or no here? So gradient of f will always give you a vector quantity which points in the direction of what? Which points in the direction of maximum increase in the scalar function. Understood? So similarly, this gradient of V here, this gradient of V results in a vector quantity which points in the direction of what? Which points in the direction of maximum increase in the potential. Yes or no? So that means it is going to result in a vector quantity, and if you move along this vector, there will be a increase in what? There will be a increase in, that means there will be a maximum increase in potential in that direction. Understood? So that means here, so that means it is going to point, it is as you move along this vector, you are going to see a maximum increase in potential. You are going to see a maximum increase in potential. That means this vector is going to point from where to where? It is going to point from lower potential to what? Lower potential to higher potential. Yes or no here? Because it is going to point in a direction in which the potential is increasing. So if you move along this vector, so the potential is going to increase. Yes or no? So that means it always points from where to where? From lower potential to higher potential. Lower potential to higher potential. Understood? So this gradient of V points from lower potential to what? Lower potential to higher potential. Higher potential. Now, what is the direction of electric field? Tell me. So electric field will always point from where to where? Tell me. Electric field will always point from where to where? Tell me. Tell me here. Electric field will always point from where to where? Parasmoon, Alok Kumar, tell me. Electric field will point from higher potential to lower potential or lower potential to higher potential? Tell me. Tell me here. Electric field will point from higher potential to lower potential or lower potential to higher potential? Tell me. Tell me here. Okay. Do you know that one or not? See, electric field will always point from where to where? It will always point from higher potential to lower potential. Yes or no? So electric field will always points from higher potential to what? Higher potential to lower potential. Yes or no? Okay. See, if you take any positive charge here, the electric field is going to point like this. Yes or no? Okay. So if you take any unit positive charge, into this field, okay, you have to do work. So whatever the work you are doing per unit positive charge, that will be developed as potential. Yes or no? So if you are at this location, so you are going to have some potential, let us say V1. Understood? So if you move from this point to this point, you are going to have some other potential, that is V2. Understood? So which one is greater? So V2 will be greater than what? V2 will be greater than V1, because as you move closer to what? Closer to the charge, the field strength is going to be more. That means you have to do more and more work. So if you are doing more work, then you are going to gain more potential. Understood? So that means the potential here is going to be higher and the potential at this point is going to be lower, and the electric field is pointing in this direction. That means it is pointing from higher to lower potential. Understood? Okay. Okay, yeah. So the electric field will point from higher to lower potential, whereas gradient of V is pointing from lower to higher potential. See, magnitude wise here, the electric field is same as what? Is same as gradient of V. So magnitude wise electric field is same as gradient of V, but whenever you are writing in terms of vectors, so the direction of electric field is exactly opposite to what? Exactly opposite to gradient of V. Yes or no here? Okay, it is pointing from higher to lower, whereas it is pointing from lower to higher. So whenever you are equating this, LHS must be equal to what? LHS must be equal to RHS. So what you have to put here? You have to put here minus sign. Okay, here just I am trying to derive the relation between what? Electric field and potential. So finally what what I got here, what I got, E is equal to what, E is equal to minus gradient of V. So here you must have what, here you must have minus sign, so that means here you must have what, you must have minus sign. So here you must have minus sign, 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 so here you must have minus sign. So if you send this minus sign to this side, I can write it as what, V is equal to what, V is equal to minus integral of what, E bar dot dl bar. So that means whenever you are writing the relation between potential and electric field, without taking the limits, so then you have to write in this manner. Why here? Because finally we are landing up with what, landing up with this expression. So whenever you are writing this expression, it is valid if and only if you put what, you have to put here minus sign. Understood? So initially we don't know whether here minus will come or plus will come, we don't know. Okay, so we have derived that here, so finally we have concluded that here there must be minus. So that means here everywhere if you have to put minus sign. So this is the relation, between what, potential and electric field, without what, without taking limits. Understood? Okay, so whenever you are writing the relation between potential and electric field without any limits, then you have to put here minus sign. So why means the reason is this one. Understood? Okay, so from where we got this relation, from here only or not? Understood? Okay, yeah. So what we have concluded here, so whenever you are writing VAB, you have to write integral A to B E bar dot dl bar or dr bar. So or you can write minus integral B to A E bar dot dl bar. So if you are having limits, you can easily tell this one. So if you are having no limits, then if you want to write the relation between potential and electric field, so then you have to put here minus E bar dot what, dot dl bar. And what is another relation we have derived? E bar is equal to what, is equal to minus gradient of V. And the work done in order to move the charge from A to B is equal to what, is equal to Q into VBA, where VBA is equal to what, is equal to integral B to A E bar dot dr bar. So once you have understood all these relations here, if you have understood all these relations, then we can solve all different types of problems based on what, based on potential energy and potential. Understood? Okay. So all these are very important here. Okay. 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 Yeah. So so up till now, so write down all these things here. So write down all this. So whatever the problems we are going to solve here, each and everything is going to based on these relations only. Understood? Now one more thing here I want to specify here is what are the units of electric field here? We know the units of del here. The units of del is nothing but what? Is nothing but per meter or meter inverse. The units of del is per meter or meter inverse. The units of potential is nothing but what? Is nothing but volt. Volt or joule per coulomb. Joule per coulomb or volt. So that means what are the units of gradient of V? The gradient of V units are volt per meter. Yes or no? So volt per meter. Understood? So that means that the units of electric field, we can write it as what? We can write it as volt per meter also. Understood? Okay. Okay. Yeah. Okay. Clear? Very good dear, very good. Okay. Okay. Yeah. So now see here. So now tell me, we have proved that electrostatic field is a conservative field or not? Yes or no? See what we got relation, tell me what we got. E bar is equal to what? E bar is equal to minus gradient of what? Minus gradient of V. So if you are able to represent any vector field as a gradient of some scalar field, then this vector field is said to be what? Then this vector field is said to be conservative field or not. So if you are having any conservative field, that conservative field can be represented as what? Can be represented as gradient of some scalar field. Yes or no? So from this relation we have proved that E equal to minus gradient of V. That means you are writing electrostatic field as a gradient of some scalar field. That means electrostatic field is what? Is a conservative field. I am talking only about electrostatic field. Electrostatic. Understood? Electrostatic field. Electrostatic field. So electrostatic field is a conservative field, and also we know that if it is conservative or irrotational or curl free, yes or no, so then curl of this E bar must be equal to what? Must be equal to 0, yes or no. So if you take curl on both sides here, if you take curl on both sides, so what you are going to get? Curl of E bar is equal to minus of curl of what? Curl of gradient of V. So from null identities, we know that curl of gradient will be always equal to what? Will be always equal to 0. So that means we are getting what? We are getting curl of E bar is equal to 0. So from here also we can say what here? Electrostatic field is a conservative field. Electrostatic field is a conservative field. So this question is very important here. So generally in IAS exams or ISRO exams or in some PSUs, they will ask this question many times here. Directly they have asked. Okay, so electrostatic field is a conservative, non-conservative, rotational, irrotational, like that they have asked many times. Okay, so here, so from here also you can say electrostatic field is conservative, So this point is very important. Okay, yeah. So now so we know that from Stokes theorem we can write circulation of E bar dot dl bar, is equal to what? How you can write? You can write this as double integral curl of E bar dot what? Dot dA bar, yes or no? So circulation of electric field around any closed loop can be represented as what? Can be represented as double integral del cross E bar dot dA bar by applying what? By using Stokes theorem. So by using Stokes theorem. Understood? And we have seen that del cross E bar is equal to 0. So that means del cross E bar will go to what? 0. So if it goes to 0, so this total RHS term will go to what? Will go to 0. So that means the circulation of electric field around any closed loop is equal to what? Is equal to 0. Yes or no here? The circulation of electric field around any closed loop is equal to what? Is equal to 0. See, it is not a new thing here. See, E bar is nothing but what? E bar, I can write it as what? Force per unit charge. Yes or no? F bar dot dl bar. So this is equal to 0. So that means 1 by q closed loop integral F bar dot what? F bar dot dl bar is equal to 0. So that means the work done, F bar dot dl bar is nothing but work done around any closed loop per unit charge. Work done around any closed loop per unit charge, we are getting equal to 0 or not? Yes or no? We are proving at each and every step, we are proving that our electrostatic field is a conservative field. So the work done around any closed loop in a conservative field must be equal to what? Must be equal to 0. Understood? Okay, yeah. Now one more thing we can observe from here is, see here, electric field, the units of electric field is volt per meter. The electric field units are nothing but volt per meter, and here for DL the units are nothing but what? Meter. So here meter will get cancelled. So that means E bar dot DL will represent the voltage, or potential. Understood? Now here what you are doing, you are integrating. Integration means what here? Summation. Yes or no? So you are summation around what? Around any closed loop. So that means closed loop integral E bar dot dl bar will represent what here? Will represent the summation of voltages, summation of voltages or summation of potential around any closed loop, is equal to 0. So where you have studied this one here, the summation of voltages around any closed path is equal to what? Is equal to 0. So that means this represents what here? This represents what? This equation will represent what? Tell me. The units of electric field is volt per meter. For dl it is meter. Meter will get cancelled. So E bar dot dl will represent the voltage. Now here you are adding up the voltage. Yes or no? You are integrating around the closed loop. That means you are adding up the potentials around any closed loop. That means the summation of all the potentials around any closed loop must be equal to what? Must be equal to 0. Understood? Okay. So that means this equation is representing what? Tell me. Closed loop integral E bar dot dl is equal to 0. Is representing that, it is saying that the summation of all the voltages around any closed loop is equal to 0. Tell me here. So that means what it is saying, what it is representing? It is nothing but what? KVL or not? Yes, very good. Parasmoon, very good here. So this is nothing but what? This is nothing but KVL. Yes or no? So this is what you are applying in your circuit theory. So the summation of all the voltages around any closed path, that means closed circuit, must be equal to what? Must be equal to 0. Understood? Okay. See, for almost all the subjects, the basic subject that you have to study is nothing but EMT. Understood? From here only you will get KVL, from here only you will get KCL, from here only you will get Ohm's law, everything, each and everything you will get from this subject only. Understood? Okay. 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 So while dealing with Faraday's law, so we will enter into time varying fields. We will enter into time varying fields. So there we are going to see that the circulation of electric field around any closed loop is not equal to what? Is not equal to 0. Okay, whenever we enter into time varying case, so that means whenever we are dealing with Faraday's law. So in Faraday's law we are going to deal with time varying fields here. Okay, so whenever we enter into time varying fields, there we are going to see that the circulation of electric field around any closed loop is not equal to 0. Is not equal to 0. Understood? Okay, so it is equivalent to what? It is equivalent to minus double integral dou b by dou t dot dA or something here. It is equivalent to minus of double integral dou b bar dot dA bar. We will see all those things later. Okay, it is not needed now. So what I am saying here is, so there whenever you enter into time varying case, so this equation is not valid. This is not equal to 0. So that means there whenever you enter into time varying case, there you cannot say this electric field as what? As conservative. Yes or no? So that's why I am specifying electrostatic field is conservative field. Understood? Okay, so if it is time varying, whenever you enter into time varying case, so it is not equivalent to 0. That means here you cannot say the electric field as conservative field. Understood? Only static electric field is conservative. Understood? Okay, so that means what here? If static electric field is conservative means, and we know that the conservative field can be represented as gradient of V, So that means this relation between electric field and potential will also valid for what? Is also valid for what? Is also valid for only what? Only static field, only for static electric field. Why? We can represent a conservative field in gradient of some scalar function, but whenever you enter into time varying case, there the electric field is not a conservative field. So there this relation doesn't hold. Understood? Okay, there the electric field is not conservative whenever you enter into time varying case. Only in static case, electric field is what? Electric field is conservative, and hence this relation is also valid, because we can represent the conservative field as gradient of some scalar function. Right? Okay. Okay. So I hope each and every point is crystal clear here. Right? Okay. So is everything clear? Tell me here. Parasmoon, Alok Kumar, tell me. I hope you will never ever do mistakes whenever they ask some direct questions like this. Okay. Up till now, is this clear? Tell me. Is everything clear? Parasmoon, Alok Kumar, tell me here. If it is clear, then we will start solving problems. Okay. So see here, I have given charges Q1 equal to 2 microcoulomb and Q2 equal to 10 microcoulomb are placed at the corners A and B, are placed at the corners A and B of a square of side 5 centimeters, as shown in figure. So this is the figure here, as shown in figure. How much work will be done against the electric field? How much work will be done against the electric field? That means they are asking the work done by the external agent. Understood? Okay. So how much work will be done against the electric field in moving a charge, of 1 microcoulomb from C to D. So here they have placed two charges here, Q1 and Q2, at the corners of what? At the corners of a square. Understood? Now they are asking what is the work needed to be done in order to move a charge. Let us say this 1 microcoulomb, let us consider this is Q3. Understood? So in order to move Q3 from where to where? From C to D. So that means they are asking to determine the work done in moving Q3 from C to what? From C to D. So that means you can write it as what? That is nothing but which charge you want to move? That is Q3. From where to where? From C to D. So that means Q3 into what? Q3 into VDC. Yes or no? Q3 into VDC. Yes or no? We know that work done from A to B. Is equal to what? Q into VBA. So you can write Q3 into what? Q3 into VDC. Yes or no? Right. Okay. So where VDC is nothing but what? Q3 into VDC is nothing but VD minus VC. So if you determine VD and VC, then you can determine the work done in moving the charge from C to D. Right. So simple or not? See, problems are going to be very, very simple here. If you understand the concepts clearly, then you can easily solve any type of problem here. Okay. So understanding the concept is very, very important. Alok Kumar, sir, how can sum of potential 0? Repeat it, sir. See, potential means what here? Potential means what? Tell me. Alok Kumar, potential means what? It is nothing but what? Work done per unit charge or not? Yes or no? So work done per unit charge around any closed loop. That is nothing but what? Work done around any closed loop per unit charge in a conservative field must be equal to 0 or not? Yes or no here? Alok Kumar, tell me. That's what I have told now. Closed loop integral E bar dot dl bar is equal to 0. Yes or no? So the units of electric field is volt per meter. The units of dl is meter. So here meter will get cancelled. We are getting the summation of all the voltages around any closed loop is equal to 0, which we call it as KVL. But if you want it physical interpretation, so E bar I can write it as what? I can write it as F bar by Q. Yes or no? F bar by Q dot what? Dot DL bar. So this represents what? This represents the work done around any closed loop per unit charge. So the work done around any closed loop per unit charge will be equal to what? Will be equal to 0 or not in a conservative field? Yes or no, dear? Yes or no? I have told this point also or not? 1 by Q closed loop integral F bar dot DL bar. So closed loop integral F bar dot DL bar will represent the work done around any closed loop. Yes or no? The work done around any closed path. So this is nothing but what? Where you are doing the work, in a conservative field or not? Yes or no? So what you are going to get? You are going to get 0. Understood? Hello Kumar, tell me here. Yes or no? Clear? Is it clear, Alok Kumar? Tell me here. Okay. Say something here. Understood, not understood. Okay. So, okay. So, work done from C to D. So, coming to the problem. So, work done from C to D is equal to what? Q3 into Vd minus Vc. Vd minus Vc. So, that means you have to determine the potential at what? Potential at D and potential at C. So, they have given Q3 as what? Q3 as 1 microcoulomb. Q3 as what? Q3 as 1 microcoulomb. So, you have to determine Vd and Vc. Okay. So, how to determine Vd and Vc here? That is the potential at D and the potential at C. So, what is the potential at D? Tell me. See, the potential at D due to what? Due to Q1, and here what is another charge you are having? Q2. Yes or no? Okay. So, the potential at D due to what? Due to Q1 and Q2. You have to determine. So, we know that, see here, we know that whenever you are having 2 point charges here, whenever you are having 2 point charges which are separated by a distance r, so then the potential at r, sorry, not potential here, what I am saying. So, I have told that the work done in order to move the charge from infinity to r is equal to what? Is equal to qq by 4 pi epsilon naught into r, qq by 4 pi epsilon into r. So, this is nothing but what? This is nothing but potential energy. This is nothing but potential energy. Yes or no? Okay. Now, potential is nothing but what? Potential is nothing but what you have to do? You have to determine work done per unit charge, that is W by Q is equal to what? Is equal to Q by 4 pi epsilon into R. So, this is the potential at R with respect to what? With respect to infinity. Understood? So, the potential at R with respect to infinity is equal to what? Is equal to Q by 4 pi epsilon into R, and I can write this VR infinity, I can write it as what? VR minus what? V infinity, which is equal to Q by 4 pi epsilon into R. We know that the potential at infinity here, what is the potential at infinity? If you substitute R equal to infinity, what you are going to get? You are going to get 0. Yes or no? So, at infinity distance, the potential will go to 0. So, in general we will represent with what? We will represent with VR. See, you have to understood, if I represent simply with VR also, you have to understood that this is the gain in potential gain in potential at R with respect to what? With respect to infinity. Whenever you are saying gain or lose, you must say some reference point. Yes or no? So otherwise it is meaningless. Yes or no? Okay. So gain means with respect to what? Loss means with respect to what? That's what you have to mention. Understood? Okay. So whenever you are doing some business, if you are saying I have gained some 1000 rupees or 2000 rupees or something like that, if you are saying gain means with respect to what you are saying, with respect to your investment or not? Yes or no? Okay. So whenever you are saying gain or loss or large or small like that, you must have some reference. With respect to that reference only, you have to tell all these things. Understood? I hope you have understood here. So V infinity is equal to 0. In general, V infinity is 0. So VR is equal to what? Q by 4 pi epsilon into R. So that means due to a point charge here, if I consider a point charge capital Q, so due to this point charge, if you want to determine the potential at a distance R, what is the potential at this location here? Is nothing but VR, which is equal to what? Q by 4 pi epsilon into what? Q by 4 pi epsilon into R, where VR represents what? VR with respect to infinity. So always you have to consider that the potential at R with respect to what? With respect to infinity. You should not forget this. Understood? Okay. So whether I will write infinity or not, you have to understand that it is the potential at R with respect to infinity. So due to a point charge, what is the potential you got here? Q by 4 pi epsilon R. Yes or no? Okay. Okay. So now I think you can easily solve this problem here. Right. Okay. So now here so work done from C to D is equal to what? Is equal to Q3 into what is the potential at D here? So here you are having Q1, here you are having Q1, here QT, Q2. Now you want to move Q3 charge, from C to D. So you have to the work done from C to D is Q3 into Vd minus Vc. So here the potential due to Q1 is how much here? So the distance from here to here is 5 centimeters. Yes or no? And the distance from B to this one is how much here? How much? The distance from here to here. See, the distance from here to here is also 5 centimeters. So the distance from here to here is nothing but what? Square root of 5 square plus 5 square. That is okay, you do this one here. Okay, so square root of 5 centimeter square plus what? 5 centimeter square. Okay, so this is the distance. From B. So I am representing with RB. From Q2 na? From Q2. Okay, so I am representing this distance as R2 here because it is from Q2. So I am representing this distance as R2. So R2 is equal to square root of 5 centimeter square plus 5 centimeter square. And the distance from Q1 I am representing with R1. Okay, so the potential at D is due to what? Is due to Q1 as well as what? Q2. Yes or no? So the potential at D due to Q1 is how much here? Is how much? Q1 by 4 pi epsilon naught into R1 minus the potential at sorry, wait. Wait here, 1 second. Now do it here. So work done from C to D is equal to Q3 into Vd minus Vc. Right. So Q3 into the potential at D here, the potential at D due to Q1 and Q2. So what is the potential at D due to Q1? Is nothing but Q1 by what? Q1 by 4 pi epsilon naught into R1. Understood? They have not mentioned anything about the medium. So if they have not mentioned, consider epsilon as epsilon naught. So this is the potential at D due to Q1, and what is the potential at D due to Q2? Now potential is a scalar quantity. You can just do algebraic addition. Yes or no? Okay, so simple addition is enough. So the potential due to Q2 at D is nothing but what? Is nothing but Q2 divided by what? Q2 divided by 4 pi epsilon naught R2. Yes or no here? Okay. Okay, so this is potential at D. So this is the potential at D. Understood? Next, minus the potential at C. So what is the potential at C here? The potential at C due to what? Due to Q1 and Q2. Understood? See, you are moving the charge Q3. You are moving the charge Q3. So in the field produced by what? In the field produced by Q1 and Q2. Understood? Okay, so you have to determine here the potential at D due to what? Due to Q1 and Q2, and you have to determine the potential at C due to what? Q1 and Q2, and you have to multiply this with what? With Q3. So you are moving Q3 from C to D. Understood? So the potential at C is nothing but what here? Tell me. The potential at C due to Q1. So what is the potential at C due to Q1? Tell me. So the distance from here to here, the distance from here to here. Okay, so let us say this is okay, name this as R3. Okay, so R3 is equal to what? R3 is equal to square root of 5 centimeter square plus 5 centimeter square. So you can do that here. Okay, so this is nothing but R3, and the distance from here to here, the distance from here to here is nothing but what? Is nothing but R4. Let us consider this as R4. Now what is VC? So VC is the potential at C due to Q1 and Q2. So that is Q1 divided by 4 pi epsilon naught R3 plus what? The potential due to Q2, that is Q2 by 4 pi epsilon naught R4. Okay. So if you do this, you are going to get the work done in moving the charge from C to D. So just substitute all the values here. Just substitute all the values and do this problem So just mathematical calculation here. Okay. So Q3. So from each and every term you can take 1 by 4 pi epsilon naught common. So Q3 by 4 pi epsilon naught you can take common. Here you are going to have Q1 by R1 plus Q2 by R2 minus what? Minus Q1 by R3 plus Q2 by R4. Okay, and if you observe, R1 is same as what? R1 is same as R4, and R2 is same as what? R2 is same as R3. Understood? Okay, so just substitute all this here, then you will get what? Work done from C to D. Right. So can you solve this problem here? Can you do these calculations? Yes or no? Tell me here. Paras Moon, Alok Kumar, can you do these calculations? Tell me here, is this problem clear? I am getting response from your side very late here. I don't know whether it is a technical issue or something else, I don't know. So is this problem clear? Yes. Okay. Okay. So with this I am winding up the session. So tomorrow. Okay. Very good. Alok Kumar Parasmun, we will do, sir. Okay. Very good. Yeah. Okay. So with this I am winding up the session for today. So tomorrow we will solve some different types of problems here, very conceptual and whatever we have learned, whatever we have gained the knowledge up till now, okay, so we are going to apply all those concepts and try to solve some beautiful problems. Understood? Okay, so tomorrow exactly at 4 p.m. here, tomorrow exactly at 4 p.m. we are going to start the session here. We are going to start the session. So today with this I am winding up the session. So tomorrow we'll try to solve some more beautiful problems, right? Okay, so until then, take care, bye bye. So if you are having any doubts, you can ask me here, otherwise we will wind up the session. So I hope everything is crystal clear. So I hope you are not having any doubts. Okay, so tomorrow exactly at 4 p.m. we will meet. So until then, take care, bye bye. Okay.